All right, everyone's coming back in. We just watched the video on our rock flow or debris flow or earth flow or grain flow or hyperconcentrated stream flow. What are we looking at here? We've got one group that's still coming back. All right, everyone's back. Oh, nope, not quite everyone. There we go. Okay, everyone's back and just watched our first video, or second video of the day, if you count the Polk County one here. What did you guys think in terms of a mass movement? What type of mass movement were we looking at? Let's go with, I'm going to call on a group. Let's go with Mira. Who was your partner?
It was me and Maggie.
You and Maggie. What did you guys come up with? What were you thinking for this type of flow?
I initially thought like a mass creep because it's like a really high sediment concentration and it was going maybe slow, but we were talking about the relativity of slow and fast and we don't know what that speed actually was.
Good. So depending on what the speed is, yeah, maybe mass creep, or if it's not that slow, what then would be your next category up? Could you remember from the chart? Yeah. So I'll share the chart again. Well, actually, what did some other group? Did anyone other groups come up with some other ideas? Sharon, how about your group? What were you guys thinking?
We looked at the video and we thought it has very low velocity, but very huge like chunks of sediment and rocks. But we couldn't remember the name because the chart was, yeah. So it was somewhere above earth flow, but not the first.
Okay.
Yeah.
Gotcha. So yeah, if I share the screen again of this handy dandy chart, I like that everyone's kind of identifying that this is a really dry flow, that we're not seeing a lot of water. You really don't see any. It just looks like dirt moving, right? It's amazing to watch fluidized dirt just moving. So that puts us probably up here in this high category of sediment by volume, probably over 80% sediment by volume. And so really slow things are going to be down here in the mass creep, and then kind of things in this range here are going to be earth flows, and then faster are going to be grain flows, and then the very fast things, debris avalanche or rock avalanches. And those generally are associated with steep mountainous environments where you have a big 1,000, 2,000 foot vertical face and you get detachment of a part of the mountain, and then you can generate these rapid speeds. Our y-axis here is key. So what is our velocity here in meters per second? And so notice, sorry, that there's a little typo. This should be 10 to the 1 and 10 to the 2, not 10 to the negative. Right here is our 10 to the 0. So this is a meter per second right here. Kind of that's kind of the velocities we see in normal stream flow, hyperconcentrated flow, debris flows. And so you can imagine meter per second, that's something moving across, you know, that in a second, well, like that in a second. So for what you're looking at, you're probably looking at something moving not quite at a meter per second, maybe a little bit slower than that, but moving pretty darn fast. So I think most people would characterize what we just saw as an earth flow. So they would call this an earth flow. And notice that there's dotted lines over here. The dotted lines are that these boundaries are really kind of rough in terms of what the actual speeds are. Remember, and this is so important with any sort of classification, like we make the classification to try and understand nature, but nature does what it wants to do, right? And so we're trying to categorize nature, and sometimes nature doesn't fit into these nice little boxes that we try and make. And so the reason that I wouldn't call this the next category up a grain flow, because grain flow actually implies that you're having individual movement of grains. And you can imagine your sand pile at the beach and grains just tumbling down the side. That would be a grain flow. And here we had big blocks moving. And so it didn't have the characteristics of a grain flow. So I would go for earth flow for this one, if that makes sense. Does everyone like that? All right. Totally agree with you. You guys like the music? Anyway, so I had you kind of see that there was some stuff in the earth flow. What do you guys think was the trigger for this earth flow? Anyone want to take a guess what this might be related to?
Maybe like spring melt or some. It looked like there was snow or ice.
Excellent, Ani. So I totally agree with you that like this, it looked like spring conditions because it didn't look that cold, but there was snow on the ground. And so probably I would agree that water in some respect it was important for fluidizing this and turning it from a mass of sediment into a flow. So I agree with you. Anyone else want to speculate as well as to like, I highlighted that there looked like there was some like equipment in that. What do you think that could be related to?
Could it have been human caused if people tried to install like radio towers in an a unstable part of sediment and they triggered that themselves?
Yeah, I like that they have human caused, and it looked like towers that you were looking at. They looked like towers, right? Those are actually cranes. Those are hunks of cranes that were entrained in the flow. And so human caused, and in this case, and this is really common, these came out of a huge mine in Russia. And so this is from Dave Peltley's landslide blog here. And he just found the video at first and was like, hey, this is amazing. I don't know what this is. And then someone emailed in from Russia and said, hey, and they found where this actual was. And it was associated with this huge mine. So here's the road right here. And so this really is common in mines where you destabilize slopes because you're digging in. And so then you mix in a little bit of water and you can trigger big debris flows. And so that's absolutely the case here. And this is actually pretty common, and something on the applied end of mass movements that I think is important is that there's ways to mine, that are better at preventing these things, and ways to mine that are not as good that will trigger landslides. And country by country, you'll have different regulations as to like how steep you can make walls and how big your mine can be and how much money you have to spend on making sure this doesn't happen. And so I know it doesn't seem like it, but here in the United States, we actually have pretty decent laws associated with mining and you know, not allowing these things to happen. And it's common in some other countries that don't have as strict laws with mining that you can trigger these types of debris, these mass movements. And this is a problem. And in this video, it looked like it was pretty innocuous. Like it would just look like the slide went out into an open field in the road and it was moving slowly. But you can easily find videos of mining in international mining companies that include American mining companies that are mining in places like South America where there are not nearly as tight environmental regulations. And what happens is you have villages that are just downhill of the mines, and you can trigger mass movements and landslides that can bury villages and kill people. So this is a really important aspect of mass movements is that applied side. And there's really actually a lot of jobs and careers associated with mitigation of landslide hazards like this. So I mentioned that because in my opinion, I like Dave and Paul's book. But in my opinion, it's geared a little bit more towards people that really want to just like study geomorphology, you know, in graduate school, and it has a different focus than this more applied side. And with mass movements, I like to highlight this because there is a lot more you can do with mass movements that wasn't covered. Like, you know, in the hill slope chapter, Dave and Paul, they spend like 3 pages deriving the soil production function. And yeah, it's really cool, and it's really helpful for maybe understanding soil erosion, but I think by doing that, they don't talk as much about these hazard type things that I think are really important as well. So that's why I bring it up, and just to let you know that these sorts of applications are out there. There's careers associated with this, and there's environmental justice issues associated with this as well. So, okay. Henry, yes.
I know you mentioned a thing or two about it, but what are some of the like general factors that make a mine better or worse at producing those?
Slope. How steeply you're allowed to stack things is a really common one. And so oftentimes when you're digging in a mine, you end up with a bunch of mine tailings or waste rock. And mine tailings is stuff that's been through processing, and waste rock is just stuff they throw out before they process the ore. And so with waste rock, you basically can build giant piles of it. And essentially that can, and what ends up happening is you have water that stacks up behind it. And so you're basically building an earthen dam holding back the water. And so we have very strict regulations as to how steep the walls can be in those earthen dams of waste rock. And basically these pits have to be lined so that water can't seep through them and cause what's called seepage failure. And so that's a huge thing. It's just regulation on the engineering side. There are known standards of how steep you can build something before it fails, and also monitoring, like how often it has to be monitored. And then another thing is responsibility as well, having laws in place that when you kill a bunch of people, that you can sue them for tens to hundreds of millions of dollars. So all of those go into providing a more safe mining environment. Yeah, great question. Okay. Other questions? Okay, let's watch one more video to do one more classification. Sound good? Okay. Here we go. Next one. All right. So it kind of, where's my, wait, were you guys watching the screen? Yeah. Okay. Okay. So it kind of said it in the title, you could probably see it, but what type of mass movement did we just witness here? What did this look like? Another earth flow or something different?
That looked like a hyper concentration flow to me, just because of the amount of water and the speed.
What do people think? Hyper concentrated or something else?
I'd agree. I mean, the size of the boulders it was carrying were pretty huge, which makes me think it was, I think the phrase was non-Newtonian.
Yes. So yeah, you get into non-Newtonian flows once you start mixing in lots of sediment. So these are actually the fact that you're moving big material gets us out of hyperconcentrated flow. When you see hyperconcentrated flow, they're just these wet slurries of mostly fine-grained sediment. So like we think of them on the sides of volcanoes associated with ashes that build up on the sides of volcanoes. This is actually moves into that next category where we've got a little bit more sediment in our fluid. This is a debris flow. And this is a classic debris flow in that they can be slow moving, which is impressive because these have non-Newtonian behavior. You can actually keep these things moving at relatively low speeds. And you can't do that with liquid water, but once these things start moving, they can have long runouts associated with them and move at relatively low speeds. Because they're so thick, they also have a very, very high viscosity. And so you can move big material in it. And you saw that in the front of these things. And this was a classic textbook debris flow that had that bouldery snout where the coarsest stuff was just getting pushed along right at the front of the flow. And so, yeah, this was a great example of a debris flow. Okay. I don't want to get, well, do we want to get into the weeds of it? I'm going to share another slide with you to kind of highlight that difference between how we think about Newtonian and non-Newtonian fluids. And so we're looking at a graph that's showing the relationship between a shear stress and a rate of deformation. So the rate of deformation is essentially how quickly our material is deforming. And are you not seeing it?
Could you share your slide again, please?
There we go. Thank you. Okay, so what we're looking at is another way of thinking about non-Newtonian fluids in terms of their shear stress, the force that it takes to make them to start moving, and then once they move, how quickly they move. And so a Newtonian fluid, what happens is as soon as you start applying a force to it, a stress, it starts to move. And so think about that. If you've got water on a flat surface, it just sits there, right? But then once you turn it on a little bit of an incline, that water starts to move down that surface a little bit. Give me a thumbs up if that makes sense. Okay, what if I take that water and I move it onto a even steeper surface? What's the velocity of that water gonna do? It's gonna go up. Yeah, so that's the rate of deformation essentially of the water. So in a Newtonian fluid, there's a linear relationship between between your shear stress and the rate of deformation. Now, non-Newtonian fluids do not have this behavior. They move differently. And so oftentimes debris flows will move in some sort of non-Newtonian behavior. Sometimes they behave like Bingham plastics. Sometimes they behave like thixotropic substances, or what we call pseudoplastics. It depends on the flow itself. But notice here what this means. Does everyone see here that with a normal Newtonian fluid, you start pushing on it and it starts moving. But here, a debris flow has a yield stress that you can push on it, push on it, push on it up to a certain amount before it starts moving. And so here, this is known as the yield stress, the amount of force it takes before you kick off movement. And then once you kick off movement, then these things start moving. So that's another way to think about these. The United States Geological Survey spends a lot of time investigating and understanding how these move. It's really important for understanding landslide and debris flow hazards. And so we've built a flume in the Pacific Northwest that we use to study these. And so if you can go work on projects like this, go get a master's or PhD or be a student intern at the debris flow flume, that the USGS has. And here we're just looking at a debris flow experiment where they're looking at the difference in runout of a dry bed, which is going to be here on the left, and then a wet bed on the right. So we can watch this. Okay, so let's quit here, stop share. That was our my example here of just showing kind of how we study these types of debris flows. They're really, really interesting and fun to think about. So yeah, it's a very active area of research, and I think that's going to continue into the future. You know, for the reasons we're going to see as more people start moving into more mountainous environments where they're going to be closer to debris flows. Our ability to understand and predict them and when they occur and how far these runouts are going to be is really important, and you'll see why that is as you start looking at the video for Friday where I talk about OSO, and then next Monday when we go over the video on LA against the mountains. So that's our classification of mass movements. We're going to take a break for lunch now, and then after we'll introduce the infinite slope model and tie it into the safety factor model. And then you'll be actually playing with Excel and developing a safety factor model for our lab this afternoon. So that's the plan. So go ahead, break for lunch. You can listen to the safety dance during lunch if you want, and then we'll come back at 1 for class. Great. Anyone have questions? All right then, crew. Great questions today. Great job working through those problems, and we'll see you at 1.
All right,
Thank you.
Bye.
Hey, Lyman.
Yes, Sharon.
For one of the quizzes,